and welcome to this video on the road to quantum reality. In this video we are going to try to establish the link between real wave quantum mechanics and the Schrodinger equation in one dimension. In the last video we showed how, much to my surprise, real wave quantum mechanics and the Schrodinger equation in one dimension could, by adjusting parameters suitably, give identical forms for the squared wave function. On a closer examination, we were able to show that the real wave quantum mechanics solution, apart from the obvious difference that it is discrete rather than continuous, differed from the Schrodinger solutions because the phase of the FRs at alternating points changed by pi radians, even though, when squared, the magnitudes were identical. Because the real wave quantum mechanics process involves the vector addition of contributions in the complex plane, contributions having phase difference of pi are effectively just plus and minus contributions. The equations which we were trying to solve in the matrix eigenvalue method, of which the equation at the top of this slide was one example, became effectively the lower equation in which the signs now alternate. We are, in fact, looking at a scaled version of the alternating harmonic function. The contributions of FRs placed in the positive x direction are -1, +1/2, -1/3, and so on. We have somehow got to show that there is a link between such a series and the second differential of the function. To simplify things, let's not worry about alpha and v for the moment. The process which we are describing is actually one of convolution. Let's have a look at what this means. The lower of the blue bands here contains the value of psi at each of the discrete points where there are FRs. The upper blue band is what is known as a convolution kernel. Although it is shown truncated here, it actually extends to infinity in either direction. We start off by placing the convolution kernel with its central zero above the psi value of interest, which in this case is psi1. Now we can read off psi1 by summing the multiplied values of the kernel and the psi at each other FR. So here we get psi1 equals -1 times psi2 +1/2 times psi3 -1/3 times psi4, and so on. Now we move on to the calculation for psi2 by simply sliding the convolution kernel across one place to the right. And in this instance we get that psi2 is equal to -1 times psi1 -1 times psi3 +1/2 times psi4 -1/3 times psi5, and so on. Convolution is a process commonly used in signal processing and image processing, although in the latter the convolution kernels are usually considerably smaller. However, the software packages used for convolution, such as in SciPy, are very powerful and highly optimized, and we can use them in doing convolution computations such as these. Now, since we are dealing with the alternating harmonic series, it is as well to know that it converges to the value of the natural logarithm of 2. This is a standard mathematical result. You can Google it for details. For us, it is important to note that the leading term is negative rather than positive. This means that the series converges to minus the natural logarithm of 2. Now let us say that we are trying to find a mathematical relationship between the alternating harmonic series applied to a discretized function and the second derivative of that function. We can begin to guess at the form of such a relationship by considering the situation where the wave function psi has a constant value of 1. In this case, we know that the second derivative has to be 0 because there is no curvature. If we consider some psi near the centre of the row of psi's, so that we can ignore end effects, we are actually going to be looking at two alternating harmonic series with negative leading terms, one coming from the left and the other coming from the right. But this sums to minus 2 times the natural logarithm of 2, and we must combine this number with the known value for psi at the point in question, which we have already defined as 1 in this case. So we can use as a trial function for the relationship between the second derivative and the convolution results something of this form. The bracketed term contains the convolved results for the point I, which we've chosen to represent as f hat star psi I divided by 2 ln2. We know that the convolution term will be negative 2 ln2 for this particular situation, meaning that the bracketed term will be 0, which in turn means that the second differential there will also be 0, which is what we want. We don't know what the beta term is. We simply assume that there must be some constant of proportionality which will make the relationship work. The delta x squared term is simply to cater for the situation where the discretization interval is something other than 1. To find the value of beta, I just used a trial and error process. I generated some reasonable looking wave functions in a symbolic algebra system. I used SymPy in Python, and this allowed me to calculate the theoretical value for the function's second derivative. Then the function was discretized over a large number of steps, say 2000, and the alternating convolution could be applied as described earlier. Incidentally, for alternating functions such as the ones we have found for psi using real-wave quantum mechanics, we could apply a non-alternating convolution, that is, just the normal harmonic series. The alternation in this case arises from the wave function rather than from the convolution kernel. It doesn't matter which way round we do it, the two approaches are mathematically identical. Then we just apply trial and error and inspired guesswork to match our trial equation to the required one, and we find the result that beta equals 8 times the natural logarithm of 2. This slide shows the results of this process for the function shown by the light blue line. To enable it to fit on the same slide as the second differential, the blue line is scaled by 1 upon 10,000. The rather messy red-blue line is in fact the plots of both the theoretical second differential and the second differential generated by our convolution process. The messiness arises because the lines are essentially on top of each other. This table compares the convolution process results and those obtained by the standard finite difference method for finding the second differential. The key columns are columns 4 and 6, which contain the percentage error as compared with the theoretical result in column 2 for the locations identified in column 1. The errors are very small. Remember these are percentages, not fractions. In general, it seems that the convolution results are more accurate than the standard finite difference method. In this slide, the percentage errors from the two approaches are compared for a different function shown in light green. The spikes in the errors near the centre arise where psi is very close to 0, so we are dividing by a very small number to get the percentage error. It is notable that the convolution process is generally more accurate than the standard finite difference, which is hardly surprising because it is using every point along the line rather than just one either side. This slide shows similar results obtained with a different function and confirms the findings. But where does 8 ln2 come from? I am reminded of this catchphrase used by a British comedian in the 1960s. I am sure the result is already well known to mathematicians, but try as I might, I have not been able to find any reference to it. But I don't know my way around the mathematical world. Anyway, in summary, we have certainly been able to show that there is a mathematical relationship between an alternating harmonic series applied to a discrete function and the second spatial derivative of the function. Or, as I pointed out above, the same relationship applies to an alternating discrete function and a non-alternating harmonic convolution. While this is satisfying, it is not immediately apparent how such a relationship is leading to the agreement between the real-wave quantum mechanics and Schrodinger results. So let's look at this now. The first thing we can do is to reintroduce alpha and v into our expressions. Remember, the alpha in real-wave quantum mechanics is a dimensionless ratio, being the ratio of the wave amplitude at the FR and the re-emitted spiral waves from the FR. It is our nonlinear interaction coefficient. For want of any better guess, I have used 1 upon 137 as the value of alpha in all of this work unless otherwise specified. Because this value is a lot less than 1, the contributions at each FR from all the others will always be negative, that is, out of phase, and also quite small. But the potential term V always gives a resonant gain to each FR. Of course, if we want to give the solution for a stable structure, it must be the case that the gains from the potential and the losses from the contributions must balance out. But V is a parameter of the problem we were trying to solve. We have no control over it. For example, in our case, V pertains to the simple harmonic oscillator potential. It is what it is. That being the case, the second differential must result from the way the structure adapts itself to the potential field. In this diagram, we have shown a small section from the infinitely extended line of FRs with constant value, which we used to find the relationship between the convolution and the second derivative earlier. We could say that at this point V must have some critical value. In the diagram, the central blue arrow represents the magnitude of the FR at some particular point. The orange downward pointing arrows are representative of the adjacent FRs, which of course have opposite phase or sign. Their magnitude will be the same as that of the central arrow, so that the green line representing the function itself is horizontal. That is, the second differential is 0. We might expect that another situation in which the curvature is 0 might arise as shown in this figure. There is no curvature because the additional negative contribution from the left hand is balanced out by the reduced negative contribution from the right hand. So we expect this situation to arise when V also has some critical value, presumably the same critical value as for the flat function. Now let's imagine the situation when V is less than this critical value. This means, of course, that the gain at this FR is smaller than that needed for the zero curvature case. The only way in which a stable structure could be maintained is if the two adjacent FRs, which are of course indicative of the entire summation of contributions, have lower magnitude than the FR in consideration. But this corresponds to a negative second differential. The curve is bending back towards the axis. The opposite argument applies when V is greater than the critical value for zero curvature. If the gain is larger, then it must be compensated for by larger negative contributions from other FRs, of which the two adjacent ones are indicative. In other words, the curvature or second differential must become positive, that is, curving away from the axis. So we can see that V and its relationship to some critical value of V controls the second differential of the eigenvectors in exactly the same way that it is controlled in the Schrodinger equation. Where potential gain is smaller than the critical value, we get negative second differential, and so psi has a downward curvature. This leads to a sinusoidal shape, which is what we find at the centre of the simple harmonic oscillator solutions. Where potential gain is larger than the critical value, we get a positive second differential, so an upward curvature. Of course, we can't have any old upward curvature because that would lead to the structure exploding. We are restricted to an inverse exponential shape, which has positive second differential, but which asymptotically approaches zero. So the link between the solutions to Schrodinger equation and the real wave quantum mechanics solutions is in fact quite intuitive as well as being mathematically demonstrable. The solutions we have been discussing were found by solving the eigenvalue equation for the alternating functions. So far we have only discussed the eigenvectors, that is, the shapes of the functions which are solutions to both Schrodinger's equation and the real wave quantum mechanics method. We have not looked at the associated eigenvalues, and we can do that now. We find that the eigenvalues are exactly equally spaced for real wave quantum mechanics, as they are for the Schrodinger solutions. In this figure, they are shown to be identical, but this comes with a health warning. The values of the parameters used to obtain these real wave quantum mechanic results are not physical. In fact, they require an alpha greater than 1. This is of course not physically possible. We are not too concerned because the one-dimensional electron is itself non-physical. Remember, we are taking contributions only from FRs along a single straight line. It is inevitable that the total contributions will be too low to balance the gains which result from V, which would be the same whether we were talking about 1, 2 or 3 dimensions. In a three-dimensional grid structure, we would expect the contributions to be much larger in relation to alpha, and thus we would hope that alpha could regain its physical significance which we have attributed to it. The key takeaway is that real wave quantum mechanics and Schrodinger are mathematically isomorphic in one dimension. We can force exact comparison of eigenvalues. There is one caveat to this statement. We mustn't forget that the Schrodinger solution is continuous, whereas the real wave quantum mechanics solution is discrete. If we tried to constrain the size of the structures too close to the wavelength of the spiral waves, we might expect strong deviation from the continuous predictions. But of course, that is exactly what happens in nature. The single particle equations fail when we try to constrain them to something like the Compton wavelength, and we are forced to move on to quantum field theory, which allows for the creation and destruction of particles. There are two main conclusions from this part of the work. The first is that we were able to show intuitively why Schrodinger's equation and real wave quantum mechanics might be isomorphic, and also to show that in the case considered here, the quantitative agreement can be made to be very exact. We also showed a more general result, mathematically speaking, that the alternating harmonic series convolution provides a general method for estimating the second differential of a function. But I am no mathematician. All this leaves us now with the next big question. Will all of it extend to higher dimensions? And we will begin to look at this in the next video. Thank you for watching. Please like and subscribe, but particularly tell your physicist friends about it.